All right, so you guys have had some minutes to find all four subspaces for this here matrix, which we shall call A, very creatively. So which subspace would you like to tell me about first?
The nullity.
Okay, so the null space of A is
-2, -1, 1.
let's see, so that's probably a vector, right?
Yeah, I wrote it in a column.
Okay, so that was -2, -1, 1. Okay, so let's think about, do we have all of the vectors like that? So probably this is going to be a span of this thing, right? So how many vectors am I expecting to have in the null space?
2.
Yeah, let me see. So why 2?
That's just how many I got.
Okay. Let's think about the rank of A. I think that's where I should probably start. The rank of A is either the number of linearly independent rows or columns, right? So tell me a story about columns here. What do you guys see about all the columns?
There's only one linear independent column.
Yeah, perfect. There's really this 1, 2 column and then scalar multiples of it, right? So I think the rank of A is going to be 1. And because you know what that one independent column is, you also just found the column space for me. And so the column space of A is the span of the vector 1, 2. You guys see that? So I know that I've got my matrix A goes like this. And in the right-hand side here, I have this vector 1, 2, looks like over 1, up 2. Span of that is this blue thing. That is the column space of A. It's just that one single line. You guys see that? Okay. Where does this thing map to and from? This thing here maps R something into R2, right? I gave away the second part. What's the domain here? Cody's actually partially got it. The domain is vectors with 3 entries, right? So that's, this thing takes R3 to R2. You guys with me?
Mm-hmm.
Okay. So the null space plus, so the dimension of the null space plus the rank should equal 3. So I think that we're short just one vector in that null space. Let's check. Is this vector in the null space? Well, if I multiply, yeah, that feels like it's in the null space. And it just did a little quick boop-de-boop-de in my head. Did you get another one you said, Grayson?
I got 2 different ones that should make up the whole null space.
Okay, give me one of the 2 you have. As long as it's not a scalar multiple of this, I don't think it'll matter.
Okay, I got -401.
-401. Yeah, so that's not a scalar multiple of the first one. So the 2 of these together, each of these is in the null space, and they are linearly independent. So, and there are 2 of them, so they must span the null space. Does that make sense? The null space being dimension 2 in this case. So I'm using the fact that I have two linearly independent vectors to say that that is a basis, ergo must be a spanning set. You guys good with that? It was a little tricksy. All right, so I got the null space. I got the column space. What's the row space? How many dimensional do I expect the row space to be?
Three?
Mm-hmm.
Oh no, I'm wrong.
Yeah, I expect it to be a subset of R3, right? So for the row space, I'm expecting that the row space should have dimension, the rank of A. Right? It's the number of linearly independent rows or columns. So in this case, what is one of the linear independent rows?
1, 2, 4.
Perfect. Very nice, Karen. 1, 2, 4. Then we could even notice the perpendicular thing. See, 1, 2, 4 is perpendicular to both these vectors. Why does it have to be perpendicular to both vectors? Well, because these ones went to 0. The only way they go to 0 is when the dot product's 0. All right. Now the hard one. Oh, I guess I should maybe in keeping draw a picture. These two things make a plane, right? You guys see that? When I span these two vectors, I get a plane. So that's a little hard to abstractly draw over here, but I'm going to just kind of label it. This is the span of my two vectors. -2, -1, 1 as a vector, and -4, 0, 1 as a vector. So those are in here, and they look like maybe that or something. Right, those are my two vectors. I spanned them. So this is R3 over here. This is R2 over here. How big is the null space of the transpose? The left null space, as it were? Where does it live? See, this is hard. It's the null space for the transpose matrix, right? The transpose matrix goes the other way. So the null space is things in the domain of the transpose. So that's going to be things that live on the right-hand side here. Let's see. So far I have the column space is blue. The null space is black. I want to make this thing green. So that thing lives on the right-hand side of the picture. And I'm pretty sure that it's got to be perpendicular to the row space of a transpose. Now this is going to have a lot of flip-flops in it. What is the row space of a transpose?
One, two.
Yeah, it feels like this span of 1, 2. Do I have the span of 1, 2 written down somewhere?
Yep, it's column space of A.
That wouldn't be a negative on one of those?
So the null space for a transpose has to be perpendicular to the row space. Yeah, which means that it's going to be the span of the vector minus 2, 1. It's going to have to sit in here like this. Oops. Damn it, stop that. Stop trying to help me. Stop trying to help me, OneNote. Notice that those two are perpendicular. Stop trying to help. Does that make any sense? That's actually the same argument, but applied to the other matrix. So the argument that we did to say that the row space and the null space were perpendicular, if I do that same thing to the transpose matrix, I find out that the null space of the transpose has to be perpendicular to the row space of the transpose, but the row space of the transpose is the column space of the regular matrix. So I get this nice perpendicular picture. This is the null of a transpose here, which we could set it up, right? We could transpose this matrix and then solve it. We'd figure out that this is the span of the vector minus 2, 1. The way I got minus 2, 1 was I just wondered what would I dot product with 1, 2 to get 0. And I know that if you switch the vectors and throw a minus sign on one of them, that works. That's cheating. Where's the row space in this picture? I don't have that drawn. What do I know about the row space? It's got to be perpendicular to what?
To the null space.
Perfect. It's perpendicular to the null space. So it sticks straight out of this plane. You guys see that? All 4 pieces, concretely drawn, perpendicularity checked, right? It's got to be. In fact, another way you could calculate what the row space is you could take these 2 vectors out of the null space and cross product them, right? Because you know there's only one vector left, and it needs to be perpendicular to the plane, so you could take those 2 and cross them. Alternatively, you could get an equation for the null space by taking this vector 1, 2, 4 and making the equation of a plane using that as the normal vector. It all meshes together right here, and it's really cool, and it's also really confusing because there's a million moving parts. So the things that I want you guys to have to remember is dimensions, and that you can always get stuff from taking spans or by augmenting a matrix and solving. You can always get things that you need that way. However, if you know the sizes and you know a little bit about perpendicularity, sometimes you can cheat a little bit. Does that make sense? Okay, cool. Any questions on this example? Okay, you guys did a nice job with this. It's hard. It really is.